回所，请启充话筒。已上锁。已解锁，请启充话筒。
Okay, good morning to everyone. The quizzes I finished marking, but we still can't discuss yet. We need to wait for other class to finish. And then, are you curious about your result? Yes, sir. Okay, maybe we still need to wait for a week next week. Okay, so we'll continue with implicit differentiation, in particular logarithmic differentiation. So last on the Wednesday we differentiate this, but there's a slight mistake here. So can you see that when this square root function here defined? So square root function defined when it is non-negative. Okay, when it's non-negative. But I put x is greater than 1. If x greater than 1, then x squared would be greater than 1. 1 minus something greater than 1 should be negative. So something's wrong here. Okay, so how should I fix it then? How should I fix it? What should my domain be? Huh? 0 until 1? About -1 until 0? -1 until 1. Okay, so in that case, we should change it to x is in between -1 and 1, which means the modulus of x is less than 1 actually. Okay. And these two are the same. Okay, well, I mean, like, y is still defined, right, if x is equal to 1 or -1. Okay, but you cannot use logarithmic differentiation to prove dy dx there. Okay, but you can use the limit way. If you are brave enough, you can use the limit way and then to see that the derivative at those points should be the same as the formula you get here. Okay, anyone try this old way here? Quotient rule or chain rule? Any brave enough so to try this? Anyone try this? And then check with the answer. Maybe you can try, see you can keep track with all the calculation. Okay, if anyone try, you can send me your answer. I can post it up with the lecture note. All right, let's continue with next function. Maybe I start a new page here. So maybe let's do one more, do together. And then the other one we will have as the exercise. So let's try one more here, 3.51. So we try to differentiate y equals to x. All right. So first you need to decide what's the domain for this function here. What's the domain? Can x be negative? Can? Huh? What is -1 over sorry, how about, is it possible to write something like this? Negative half to the negative half. Is it possible? Huh? No, right? Okay, so negative won't work here. So 0 over 0, I guess, depends on what context you want to discuss. Could be different thing. So really, not that y greater than 0 is defined for x greater than 0. Okay, so we are fine. If x is greater than 0, then the whole thing will be always greater than 0. So ln will work for points that are non actually positive. Okay, so then applying logarithmic logarithmic sensation. Okay, so we get ln of y equals to ln x. Okay, but we can pull the x down. So let's put the x down, the power x. Okay, then we can use implicit differentiation here, such that we can differentiate everything with respect to x. So which variable is implicit here? So the variable that's implicit here is x. Okay, so y is implicit in terms of x, right? Okay, so differentiate ln yx with respect to x. So this has to use chain rule. Yeah, so if you use chain rule, what you will get is you differentiate ln over yx, so you get 1 over y, and then you differentiate y, you get dy dx. Okay, make sure you know how to use chain rule, because we have decided that it's better that you write down what's u, what's y, what's u, okay, before you do the chain rule, or when you do product rule, make sure you write the u and v proportion rule. Okay, so make sure you, yeah, if you want to earn marks, please write down, for example, like w equals to ln w, sorry, ln maybe u, then u equals to yx, y like that. Okay, so you can do the chain rule, dw dx, sorry, dx equals to dw du times du dx. So if you want to earn the marks, please write down what's the substitution you make. Okay. Okay. How about the next part? So next part is a product of function, right? X times ln x. So you should use product rule. That side. So if you use product rule, in one term you get x over x, the other one you get x. So here I'll say it's a chain rule plus a product rule. Okay, so the product rule that we use here was u equals to x, and then v equals to ln x. And then you check what is u prime, and then you check what is v prime. Okay. All right. So dy ds is just y to the 1 plus ln x, but y we know that is x to the x. Then multiply by 1 plus ln x. Okay, so far, any question? Straightforward. Okay, question. Feel free to ask. No need to be embarrassed. Okay. All right. In that case, um, let's look at this question. We won't do it, but let's discuss why we can apply logarithmic sensation here. So y equals to x squared plus 1 sin x. Can we use logarithmic differentiation here? Can we do it? Okay, so I shouldn't write like this, huh? It's better that I rewrite again. Okay, can we differentiate this y or not using a logarithmic differentiation? Meaning, yeah. Okay. Can we use the logarithmic differentiation method? Why? Why can we use it? 加同. We use logarithmic differentiation to find the. So when does the logarithm function define? Can you tell me when does the logarithm function define? Not yet, not yet. Just listen to my question. When does the logarithm function define? Y equals to log x. So log x, x when is non-defined. Positive, right? Okay, so if you want to apply log to this y here, you need to make sure that everything here is positive. Okay, so when is this function defined? This function seems to define it everywhere, right? You can put any x into x squared plus 1, and then you get some value. And then you take to the power of sine of any x. What do you get? Sine of any x. Sine x is ranging in between -1 and 1. Okay. But if you take power to -1 and 1, does it change your sign or not? Your power, does it change your sign? What is power -1? It's just reciprocal, right? Okay, you won't change your sign. But the x squared plus 1 is always positive. Okay, so this whole thing is always positive. Okay, so you can do the logarithmic differentiation. Okay, so you take ln on y and then ln on the x squared plus 1 to the power sine x, and then you differentiate. Okay, then you find your dy dx. Okay, make sense? Question? Got question? Question? You a bit confused, you? You okay? Okay, okay, okay. Sure. In that case, we will skip this. So please try and do at home. I will provide answer. So someone, I think, helped to check my lecture note, but he is not here yet. So whenever you found any mistake or calculation error on my lecture note, right, please contact me so that I can correct it, so that others won't get confused. Okay, so using the uh, limit or the derivative we know on exponential function, actually we can derive these two limits here. Okay, I won't do the derivation here so that I don't want to confuse you. But make sure you know this limit here. This is a very useful limit. So what is limit of 1 plus x to the 1 over x? Okay, in principle, this is really hard to compute. So you are taking like 1 over the power to the reciprocal of x. So it's like very hard to imagine this function even. Okay, but it turns out that if you take limit to 0, you get e. Okay, so similarly, you can replace this x with 1 over n, so that if 1 over n go to 0, meaning n will go to infinity. So there's something I want to remind you. Please don't ever write this in the mathematics course. Did you get this from your high school? High school. So did you realize that we say that infinity is not in real number? So you can't really do the division. Yeah, so please don't write this in any exam or in any class, in maths class here. Okay, please don't write this. There's nothing like this. Okay, unless there's a limit. So what you only know is this. Okay, and then this thing is not 1 over infinity. Okay, although sometimes we speak verbally, is like, oh, we take x to infinity. We are not really replacing the x with infinity. Yeah, we are describing a behavior here. This behavior. Okay, when x go to infinity, it get very close to what's this line? Y equal to 0. So you get very close to y equal to 0. Okay, it's not really evaluating. And there's no substitution rule on no substitution rule or property on x equals to infinity. And x cannot equal to infinity. Okay, right. You cannot say my function is continuous at infinity. Can or not? Where's infinity? I cannot touch. I cannot touch infinity. Okay. Although we say that a limit law will hold when you do limit to x to infinity, but you can't really do continuity at infinity. You cannot touch infinity even. Yeah, please don't write this. Yeah, so another thing is maybe in high school you learn a lot of calculation, right? Maybe some of the step is illegal. Okay, but it just help you to kind of get the calculation. So when you come to university, right, you will learn that what is illegal, what is legal, and what's the proper thing to write down. Okay. Right. So given these two limit, right, we can play some variation here. Okay, we can play some variation here. Maybe just some very quick limit exercise. So let's say we know these two uh, formula here. So how do we compute these two things here? Okay. So there's some trick. Maybe it's worth to learn here. Maybe it's some trick to learn here. Okay, so there are two kind of limit we want to compare to. Maybe bring them down. Okay, so we want to decide which one is easy to use. Maybe one could think that it's very close to the second one. So we try to make it as similar as possible and then see if we can apply the formula. Okay, so one thing we could do is what? We just divide by n. Okay, but there's some difference here, right? So one of them is 1 over n, the other is 2 over n. Okay, so how do we make it like a 1 over something? Okay, so one way to do that was you push the numerator down to the denominator, something like that. Okay, but it's not close yet, right? Because the formula is all over the variable part is n. But now you got n over 2. Uh-huh. N over 2. So can we make them uniform variable? Let's say y was over 2, right? So can we make them uniform? So it seems like we cannot change the denominator any further, right? But maybe we can change the power or change the way we take the limit, right? So first, maybe one can realize that we can make it 2 times n over 2 for n, meaning you take products of two same kind. But how about the variable? If n go to infinity, does it imply that n over 2 also go to infinity? Right. Okay, so we can change the way we take limit. Okay, instead of taking n to infinity, we take n over 2 to infinity. So in that case, we have the product of these two things here. Okay, since the limit exists for this product, we can calculate it as a product of limit. Okay, so what's the answer? Anyone realize what's the answer here? Who is beside Jia Tong? Jia Tang? What's your name? Jing Jie. Okay, Jing Jie. What's the answer? What do you think? Sorry? What square? E square. Okay, thank you. So E times E equals to E square. Okay. How about next one? Next one is also quite fun. So we play the same game. Uh, play the same game. We simplify the quotient such that we get 1 minus 2 over n. Okay. And then maybe what can you do next? Do we still play the same game? Like 1 over, let's say 1 over negative n here. Is it doable? Maybe you find stuck. Or you can continue if you can get it. You can let me know. At least I find stuck here. Okay, so what's the other way we can try? There's another formula to use, right? If you know that something go to 0 and then the power go to infinity. So the nice thing about this limit is anything inside the bracket, right, is approaching to 1, but the power you take is infinity. So you might think that 1 to the infinity should be 1, right? But it turns out to be e. Okay, sorry. Oh yeah, thank you. Yes, thank you. Maybe you can try this. Okay, so you see how the significance of this limit is if you just plainly think that this x will go to 0, okay, and then this 1 over x will go to infinity, it's like 1 over infinity, right? But here is not 1, here is e. Okay, so there's something non-trivial happen when you take this limit here. Okay, and then well, so how I gonna do this? Instead, I'm gonna use the first one. Okay, I'm gonna use the first limit here. So instead of bringing the 2 over n down, I will just keep it. Yeah, I will just keep it. But instead, I'll do something else on 1 over x. On the power part. Okay, because I know that the second part here is going to 0. So can I make the power going to infinity? Well, it is going to infinity, but I want to make it the same variable. So I could put negative 2, 1 over negative 2 over n here. Okay. Is this n? Everyone get it? Is this n over this n? Is this power n? Negative n over 2 times negative 2. Okay. So from here, again, we can write it as negative 2. So also realize that n go to infinity implies that negative 2 over n go to 0. Okay, so we can change the way we take limit. And then we have 2 of this thing here. 1 over n. That's going to be 2 over negative. Wait, let me see. Yeah, so -1 over 2. Okay, so we get e to the -1 times e to the -1. Okay, any question so far? Question. So these are just some tricks. Just some tricks that how you manipulate the fraction or the power, okay, so that you can use whatever formula that's known to you. Okay. If this is good, then we will continue to the last part of this chapter here. Okay, let's continue to the last part of this chapter. This rate of change, is it worth to discuss? Let me see. Okay, let's quickly do this rate of change. I think we at the start of the differentiation, we already discussed that we can realize derivative as a rate of change of something. Okay, so in particular, this example give you a position, okay, position function here. So these particles will follow the cubic polynomial t cubed minus 6t squared plus 9t. Okay, so if you're gonna find the velocity, you just differentiate it. Okay, and so this is your velocity. Another way to write it is ds over dt. Okay, so these are all the equivalent way. So if you quickly compute it, it's just 3t squared minus 12t plus 9. So what's the velocity after 2 hours? Sorry, 2 seconds, 4 seconds. So you need to make sure the unit we use here pair up with the question. So this x is measured using meter, t is second, so you can just do substitution without conversion. Okay, sometimes the question record in minutes, ask you in seconds, so you need to be really, really careful here. Okay, so well, you just compute what is Vx, V2, and V4 here. Okay, then you will get the answer. That should be straightforward. I think we don't need to compute here. So when is the particle at rest? So what does it mean by resting here? If you rest, do you have velocity? Zero. Okay, your velocity is zero. So basically, you need to find what is Vt equals 0, and then go and find what's your t. Okay, very straightforward. So when is the particle moving to the right? Okay, so here there's a left-right problem here, right? So if you remember in your physics, right, displacement to be negative. Okay, so there's a direction here. So actually we are assuming moving to the right is moving in positive direction. Okay, so in picture, so if you move to the right is positive, move to the left is negative. Okay, so moving to the right here, moving to the left here, do we refer to the positive displacement or positive velocity? Hmm? Sorry? Yeah, I asked you something. So do we refer to a positive displacement or do we refer to a positive um, velocity? Huh? Someone murmured. Sorry?
Like the velocity and displacement
Ah.
together is if to the right is also together positive.
You said together.
Direction like a vector.
Uh-huh.
If positive together should be
Okay.
both should be like
Okay.
positive direction.
Okay, let's think about it, right? Let's think about it. So if you say that both have to be positive,
Yeah.
direction and velocity have to be
Yeah.
positive. So can I let me think. So how can I put it? So displacement. Okay, so how about like if your displacement is like negative 10?
Like
So if you think about it, so if your displacement is like move negative 10, but I move to the right 2, but your displacement is still negative, right? But you actually moving to the right already, right? Does it make sense or not? Okay, so your displacement could be still negative, but less negative. Right now, less negative. So actually, we are referring to just the velocity. Okay, the change. Okay, the change to be positive. Okay, VT to be positive is enough. Okay, so if you write uh the what's this quadratic function that we have worked out here is just 3 times t minus 3 times t minus 1 greater than 0. Okay, after factorizing. Okay, so how do you pick the time? Did you learn how to choose inequality here? Inequality for t here. So because this is a quadratic, right? So you could draw the smile face or the sad face, right? Is this how you learn in high school? Smile face, kind of. Okay, so because it's a positive on a t cube, t square, so it's a smile face. And then you label the two roots here. So one is 1, one is 3. So if you want the greater than 0 part, you should choose anything less than 1 or greater than 3. Okay, if you are not sure, you can just put numbers in. Okay, just put numbers in. So basically, this this quadratic here split the number into like 3 regions. Okay, so you test your numbers. Okay, for example, when t less than 1 is maybe you can take 0. So you put 0 in here, then negative, negative cancel, you get positive. How about here? If t is 4, then these two numbers positive, so positive and negative is still positive. Okay, but if you pick anything in between 1 and minus 3, what do you get? You will get always negative on the t minus 3 side. This but t minus 1 is always positive. Negative, positive become negative. So that one is less than 0. Okay, so we will pick that. We will pick t less than 1 or t greater than 3. Okay, here is using second. 1 second, 3 seconds. All right. Okay, so you might wonder why we have so many parts of this question here. So the really key boss of this question here is this. Find the total distance traveled by the particle in the first 5 seconds. Okay, you have to find the distance here. Okay, but you are given displacement actually. Okay, so can I just compute x5? Can I just put 5 into it and then get the distance? Why not? Why not purity? Just some simple explanation is fine. No need to be too detailed. What happens if I just put 5 into it? You don't know how to explain. So do you think that you might calculate something less? Because it's a displacement, right? Something that cancel inside me. Because you got a positive, negative, positive. It's like displacement is like it's like the result of your moving. Right or not? So you move there to set, move back to set. So after 1 second, you move nothing. But actually, how many steps you move? You actually move something like this. Right. So what's useful here is the modulus function. So modulus function will help to remove these signs. Where you remove the negative direction so that it may become positive. So it contribute to how much you move. Okay. So how do we put this? So how should we put this? Well, so what do we know? What do we know? So from this from this quadratic function we drew just now, right? What do we know? We know that, okay, so well, so let's fix our t in 0 to 5. Okay, so let's draw this timeline up. So let's see what happened. Okay, so how should we draw this? So from 0 to 1, the particle moved to the right position. Okay, this is what we know just now. Okay, but what happened to 1 to 3? 1 to 3, what happened? It moved in the negative direction. Okay, so it moved to the left. Okay, but how about 3 to 5? Again, move to the right. Okay, so this is from the D part we know just now. So how this particle move actually? So you go to the right, and then you go to the left for 3 seconds, and then you go to the right like that. Okay. So if you use displacement to compute, right, maybe you go to the same place or not very far from the original place. But then how do you compute this? So you really need to make all this part as a positive distance so that you can add them together. Okay, so then how we should do here? So the total distance is actually, so here not fixed, here consider. So what's the total distance? The total distance is, you take the end point, okay, minus the starting point, but I want to contribute a positive contribution of this part. Okay, and then I take another endpoint, f3. So our point is x, right? So here's x. x3 minus x1, okay, and then plus s5 minus x. Okay, then you do this computation. Add all the path you walk positively. Make sense? Okay. Okay, I leave it for you to compute. Is it fine? Can get it? Question? Is it Margaret at the back? Margaret, can understand? Good. Okay. Okay. How about acceleration? You just do dv of dt. Okay, just do dv dt. You differentiate once more. Okay, you differentiate once more. Okay. Now, here becomes speeding up and slowing down. So the question asks, when is the particle speeding up or slowing down? So in real life, right, people ask you, when do you speed up? When do you slow down? Can you explain using velocity, displacement, or acceleration? What do you think? Can you explain? When do you speed up? Obviously, acceleration has to be positive. Wait, say again, sorry. Say, mhm. Okay, sure. Okay, good. Okay. So you say that it speed up when acceleration is increasing, right? Okay. So is it right or not? Let me see here. Is this the only case? Is this the only case or not? But the negative positive, what does it refer to actually? The positive or negative of acceleration, what does it refer to? Huh? The former one? Okay. Okay. So you mean someone told you it's like that? Okay. Sure. Okay. So let's try and figure out whether it's true or not. Okay. Let's try and figure out it's true or not. So if velocity is positive and then it's increasing, then acceleration is increasing, then kind of speed up. But is it possible to speed up in a negative direction or not? Just now we mentioned that when velocity is positive, you move to one side, right? Negative, you move to the other side. So it's like negative velocity is not like very slow. It's just going to the other direction. You get what I mean? Because usually -2, you might think that it's very small than 2. But it's not the case for velocity. It's just that you move to the left side with the speed 2. Okay? Does it make sense? So we can accelerate in the positive direction. We also can accelerate in the negative direction. Okay, we can also accelerate in the negative direction. So actually, when the particle speed up, it means that your velocity is positive and acceleration is also positive, or your velocity could be negative and your acceleration is also negative. Okay. So meaning a particle will speed up if velocity and acceleration have the same sign. So if it slow down, then it will have opposite sign. Okay. Slow down if VA have sign. Okay, because your velocity is moving one direction, but your acceleration is moving the other direction. Okay, so you slow down. Okay. Yeah. Okay. So how to figure this out? You should plot the graph. You can plot the graph. Otherwise, I think it's very hard to compute. So if you plot the graph, this is the graph. Okay, so you got S, and then you got B is the blue line, S is the red line, A is the acceleration. So your acceleration is linear actually. Okay, so when do they have the same sign and different sign? So we compare B and A. Okay, if you compare B and A, so you can start from 0 first, okay, start from 0. And then 0 to 1 is a positive on B, okay, but your acceleration is at the negative part. So it slow down, okay, but your motion is going to the right. Okay, so this is your motion, this is your slow down or speed up. Then when A go to the negative, okay, from 1 to some point here, some middle point here, but your acceleration is still negative, so this part speed up. Go to the other direction but speeding up. Okay, go to the right, slow down, and then go to the other direction, speed up. Okay, and then while moving to the other direction, speeding up, but then what? The sign of A and the velocity become opposite again. So you speed up on the other direction and then slow down. And then speed up on the other direction. Yeah, forever. Does it make sense? Does it follow any motion that you know? Any motion you see before? Does it mention any motion you see before? So you go to the right, slow down, and you straight away jump to the left, and then slow down, and then go off on the other side. Okay. Okay. Yeah, so this is about this. I think there's some application question we could discuss later, but hopefully we won't discuss all of them. Depends. Yeah. Okay, if we can finish earlier chapter 3, we might start chapter 4 today. Okay. Any questions so far? Question? I think this part of application part maybe is more relevant to your degree or to your course, because whenever I teach mathematics course, right, maybe to like DMT, AIT, SW, right. So for the non-MNT degree, they will ask, why do I need to study this? You ask why do you need to study something? You confused or you just learn whatever we give you, you learn. I think this is good, but you should also ask yourself why you learning it. Okay, if you cannot use in your real life, then it's really useless. It's really useless. But sometimes, right? Let me advise you. Sometimes you won't use it directly, but at least the idea, okay, the idea you learn should be able to generalize to different field. Okay. Yeah, the idea you learn should be able to generalize to different field, at least. Okay, maybe not the derivative, but the idea of the derivative could be used in different part that you work on. Okay, got question? Any question? No? Okay, if no, let's break until 9:58. Yep. Yeah.
To ask about
Sorry. Yeah, yeah, yeah.
as find the velocity
Yep.
at the field.
Yep, yep.
Does that mean that we leave it as the derivative
Yes.
or we solve for t?
There's nothing to solve for t, right? Because it doesn't tell you what's the specific velocity or any time t. So you just at time t, meaning at any time t. So you need to solve it as a function. Okay. Yeah, unless in this question it tells you what is t. I want 2 seconds. I want 4 seconds. At time t, usually people say general, like anything.
So you just leave it as the
Yes.
derivative.
Moving to the right. So actually, there's an assumption we make here. Maybe we should include it to the question. Meaning, moving to the right just means that the okay. First of all, moving to the right is a positive direction. Okay, I mean move. I mean, how to say? So right direction is a positive direction. So now is a moving to the right part is we will use velocity to decide it whether you move to the right or left. Okay, so because I think we should. I think people should be confused as well. So maybe later I can explain again. So what is velocity? Yeah. So vt v dv dt dv dt. Okay. Change of x is v. So let me think how to put it. T is x and t2 t1 over t2 minus t1. So let's say t2 is greater than t1. Okay. So this is like the This is not instantaneous velocity, but this is average velocity. This is the velocity you learn in physics. Okay, so um, so you should think that this t2 minus t1 is always positive, right? But how about this one? This could be positive, this could be negative. Okay, so when is it positive? When is it negative? And this one is greater than this one. But in our case, right, what does it mean by x to be positive? What does it mean by x to be negative? So x positive should be moving to the right. Okay, then so you should imagine like there's a line here, 0. So you move here is positive, move here is negative. Okay, so if the changes is positive, maybe meaning you move more to the right. If the changes is negative, then meaning you move more to the left. Okay, so this velocity will keep track. The sign of this velocity will keep track. You move to the right. Move to. Does it make sense? Yeah. Okay. Yeah, this one. Okay, good. Speeding up meaning the velocity get faster, 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 faster. Okay. So to keep track of the changes of velocity, right, is we use acceleration. Okay, we use acceleration. But acceleration, there are two kind of answer, right? It could be positive as well, it could be negative as well. So we need to interpret which one is speeding up, which one is slowing down. Okay. So similar analysis here. So delta t is like sorry, delta v. So average acceleration is like v of t2 minus v of t1. T2 minus t1, right? Okay. So um so similarly, what you would think is, so how should you interpret positive, negative here? Okay, so like we said just now, if V is positive, that means we move to the right, negative move to the left. But how about their difference? How about their difference here? How about difference? How about the difference? So if you move to the left in one direction, one velocity, move to the right in the other velocity, and then you take the difference, what happened next? So it's still about direction, right? It's still about direction. So delta V tells you in what direction this velocity increase. Okay, so if it is positive, then it increase on the right side. I mean, you move to the right faster, and then on the other side, you move to the left faster. But the question is, it is possible that V is positive, A is negative. V is so there are a few cases could happen, which is, how should I put this out? So VA, there are four things could happen: plus, 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 minus, minus, plus, and minus, minus. Okay. So your velocity, if your velocity is moving to the right, your acceleration also moving to the right, then you are speeding up to the right. But if you are moving to the right, but the changes of velocity is moving to the left, so you want to run, but your changes is like going to the other side, so it kind of slow down, right? And then, but if your velocity going to the left, but your acceleration is like the changing is going to the right, then you will slow down your velocity.
So it
Yep.
builds up when they're the same.
Yes, exactly. So this is what we written. Yeah. Yeah. Okay.
Yeah.
Okay. Thank you. Let's take one list of table first. I mean attendance. 唐熙和 OK，陈乐天、陈瑞阳、陈若石、陈思曼、陈思曼、陈一南、一南、陈一南，那也一南，玉涛、陈玉涛、陈玉涛、陈玉涛，Did you receive my Teams message? You check your Teams message. Yeah, you submitted wrong file to the quiz. Please submit as PDF, not Word. You understand? Why not Word? Because we cannot do annotation on Word. If PDF, we can just mark it. Word, you need to type. You understand? What do you mean face to face? Cannot also. Yeah, we don't accept. So you need to scan it. I mean, you can use Word to save as PDF, right? Yeah. Okay, so please save as PDF. Yeah, Yu Tao, did you get what I said? Yeah, please don't submit as Word. Okay, save as PDF. Chen Yizhe, 戴立文、邓瑞阳、方泽汉、卜家来、何嘉诚、吴嘉怡、黄启军、黄义庆、季俊义、Frank 俊义、孔相思 got it. 雷艺林 Yeah, Yiling also, right? Please don't submit as a word, both of you. Okay. Did you get my Teams message? Yes? Okay. Li Bingzhen. Okay. Lin Haoyun. Okay. Li Jiatan. Lin Wenqi. Liu Hangxiang. Liu Junjie. Liu Xingyang. Lu Wanda. Okay. Lu Xingyue. Guo Yuhen. Ma Yitian. Okay. You are Ma Yitian. Miao Bingchen. 倪浩然. Okay, how about let's start first, continue attendance working later. Okay, so just now, Purity asked a question about still not understanding about this moving to the right or left thing, right? So you should think about the velocity we define, okay? So if we don't use the limit way to describe it, just look at the average velocity, okay? How do you compute the average velocity? We are using the final displacement, taking away the initial displacement over time. Okay. So we define that the displacement to the right is positive, to the left is negative. So meaning what happens if this difference is positive? If the difference is positive, meaning what? You move more to the right. If it's negative, then you move more to the left. Okay. So this velocity will tell you either you are moving to the left or to the right using sign. Okay. Does it make sense? Does it make sense? Okay. So similarly for the acceleration, okay, so you take the final velocity as the initial velocity. Then if the velocity is positive, at that point, and then acceleration is also positive, so meaning you are going to the same direction. So you move to the right, and then you accelerate. You change. Your changing is also positive. But if you're moving to the right, but your changes is moving to the left, what do you think? It's like dragging you, so you kind of slow down. Okay, you are moving to the right, but your changes is going the other direction, so you slow down. Does it make sense? Okay, so as long as velocity and acceleration has the same sign, then they all move in the same direction. So when does your particle neither speeding up or slowing down? When? Huh? What? Yeah, answer when? When the particle doesn't speed up or slow down. Oh. Huh? When? Oh. No. It doesn't speed up or slow down. Doesn't speed up, either speeding up or slowing down. Just acceleration equal to 0. Yeah. Okay. It could still moving, but moving in a constant velocity. Or it could just stop. Yeah, two possibilities. Okay. Let's continue. Okay, so the second last part is about this related velocity here. So what's related velocity? So meaning there's various things that depends on t. Okay, but these various things are controlled by a function. And these are called the related rates here. So I mean one of the related rate you see was chain rule. Okay, chain rule is one kind of related rate. And then the other one is implicit differentiation. Okay, you get y in terms of something else, and then they all depends on some variable x. Then you want to differentiate over. Okay, so let's try this. Okay, let's try this. Let's try this. So if A is pumped into a spherical balloon, for this kind of question, right? Make sure you know how to draw it. So please draw your question. So spherical balloon is like just draw spherical. Just draw a sphere. So your air is bumping through this sphere. So maybe something like that. So that its volume increases at the rate of 100 cm cube per second. So what does this mean here? So this means that dV over dt is equal to 100 cm cube per second. So how fast is the radius of the ball increasing? Okay, when the diameter is 50 cm. Okay, so the question is about dr dt. Okay, at the diameter equals to 50 cm. Okay, so you see, the information is about v. The question is about r. Do you have any way to relate v and r here? Volume of sphere with the radius of sphere. Do you know any formula that relate? What's the formula? V equals to 4 over 3 r cubed. Okay, so this is the volume of what? Sphere. Volume of the sphere. Okay, so actually this is V r equals to 4 over 3 pi r cubed, right? Okay. So you know V in terms of r, you know dV dt, you want to find dr dt. Is it possible based on what you have learned before? Is it possible or not? you have dv dt, you have v in terms of r, you have to find dr dt. Is it possible? Maybe I put in some form, maybe it can remind you a bit better. dt and then dr dt. What else you need? What else you need? Maybe like this. Does this remind you of anything? What's the thing you should put in front dr dt? You got dv dt, you want to find dr dt. There's some missing piece here. How do I make this equation works? What's the thing I should put here? Any idea? Any idea? 玉衡 is it 玉衡? Someone call 玉衡 or not 玉衡 meh? What's the name? Yeah, 罗玉衡 You are 玉衡 right? You no idea? Okay. Right. Yeah, dvdr. If I put dvdr, what's this? What's this equation doing? What's this? Cancel. Not really cancel. What rule is this? Chain rule. This is chain rule, right? This word, right? This is chain rule. So this is by chain rule. Okay, this is chain rule. Okay or not? Okay. So the problem here is, can you get dvdr? Is it possible to get dvdr here? Just now, what's your name again? Gabriel, right? Is it Gabriel? Yeah, Gabriel said that v is equal to 4 over 3 pi r cubed. Can we get dvdr? Huh? Can? Oh, no. Can, right? So what is dvdr? dvdr equals to d of 4 over 3 pi r cubed over dr. Okay, then what can we do here? We can do the linearity d over dr of r cubed. How to differentiate r cubed? You get 4 over 3 pi 3r squared. Okay, so all together you get 4 pi r squared. Okay or not? Make sense? Okay, so then what? Then you can substitute your assumption in by assumption. dv dt is 100. Okay, and then dv dr is some formula 4 pi r squared times dr dt. Okay, which means dr dt equals to 100 over 4 pi r squared, which is 25 over pi r squared. But you see, this dr dt depends on radius. Okay, depends on radius. Do we have any desired radius here? What kind of radius we want? Where do I want to check about radius of balloon increasing? 25. Why? Because it was given the diameter. So diameter is 50 centimeter, implies that the radius should be 25 cm. Okay, so it should be at radius equals to diameter over 2, which is 50 over 2, which is 25 cm. dr dt is 25 over pi times 25 squared, which is 1 over 25 pi cm per second. Okay. Yeah. Any question? Question so far? So you see, we get the V in terms of R, but this R will change again with T. Okay, so actually what you have here was V in terms of RT, and then R in terms of. So they are like two variables to describe this. Actually one, but T will decide what's your R and then decide what's your. Okay. Question? Any question? Any question? Question? Purity, okay. Yeah. Cannot see. Which part you want to see? Last part. Like this. Got it? Okay. Can follow? Okay. This is a calculus scan. Okay. Question? No? Okay. So let's continue. How about this one? So a balloon is released at a point of 150 meters away from a observer. So let's draw this situation here. So you got to observer, okay, on the level ground. So and then there's a balloon release. There's a balloon release or balloon release. So it is like 150 meters away. So if the balloon goes up at the rate of 8 meters per second, so let's call this a variable h. Okay, then dh. So let's write here dh over dt. Sorry, just this one. So dh over dt is 8 meters per second. So the question is how fast is the distance from the observer to the balloon increasing when the balloon is 50 meters high? So what does it mean by distance from the observer to the balloon? How should we measure this distance? How should we measure? Do you like go to 150 and then measure the height? No? So how? Just directly go from the observer to the balloon. Okay, so we just directly go from the observer to the balloon. Let's call this x, s. Okay. So the question is you want to find what is ds dt, okay, at height is 50 meters. So you are given height, you are given 150 meters, and then you want to find s ds over dt. Any relation between these three things? Any relation between these x, h, and 150? What? Huh? What? Right angle triangle, meaning the Pythagoras theorem. Okay, so not that. So in a proper writing, right, you should say like let x be the displacement or the distance. I think distance is enough, no need displacement, because you won't, there's no wind blowing here, so you won't no need to worry about that. So it was just moving out, however. So let x be a distance between the observer and the balloon. Let's save the time. Okay. And then let h and also h be the distance between, okay, distance of balloon from the ground. Then we can do all these things. Okay, so by Pythagoras theorem, we know that x squared plus 150 squared is, sorry, wrong way. H squared plus 150 squared is x squared. Okay. Then here, everything could be in terms of t. Okay, so we can do implicit differentiation. Okay, after you do implicit differentiation, what do you get? 2s ds dt equals to 2h dh dt. 150 is a constant, so I get to 0. So from here, we get that what do we want to find? ds dt is equals to h over x of dh dt. Okay, but by assumption, what do you know? You know that dh dt is always 8. Okay, h over x is always 8. But you want to, what h you want to find? You want to find at 50 meter. Okay, so you need to replace your h by 50 meter. But then, do you know what's s here? You know at the 50 meter, what happened to your s? Any idea? At 50 meter, what happened to your s? This dh dt is always 8 meter, and then h is 50. Can you get s or not when height is 50 meter? Your height is fixed. Then by Pythagoras theorem, you can find your s, right? Okay, so from here, when h is 50, what's your s? S is equals to square root 50 square plus 150 square. Can someone get what is this? Sorry? 50 times square root 10. Okay. Okay, 50 times square root 10. So here is 50 times square root 10. Obviously, we don't want to take the negative one. Okay, so this is just 8 over square root 10 meter per second. Okay. So far, so good. Question. Want to zoom in? Last part. Yeah. Okay. Okay. So actually, to be precise, maybe I should put here this DSDT is evaluate at the hash equals to 50 meter. Okay, then you get this. Okay. Any question? Please don't just copy down. Understand what I wrote here because I'm gonna post this anyway, so you can go back and copy yourself. But the point here is you have to understand what I say. If don't understand, you can ask. I won't get angry at you. Okay. Good. Okay. Next question is similar. If it is similar, then we just discuss what we need. So this question is similar. Water is pouring into a conical tank at a rate of 8 meter per second. So starting from here, you can start draw already. So what's conical tank? So you should know what's con. Con like that, right? And then at a rate of 8 meters cube per second. So meaning this cube means what? Cube is a volume. Okay, so actually it's a volume of this the volume of the conical tank. Okay, then the question give you dV over dt is 8 meter per second, 8 meter cube per second. Then you have a height. So there's a radius here, and similarly there's a height here. The height is 12 meter, and the radius of its circular opening is 6 meter. Okay, so we are doing it right. So here is the opening. So your water will fill it in here. How fast is the water level rising? Okay, when the water is 4 meter deep. Okay. So you want to find what is dH at h equals to 4 meters. Okay. So anyone know what's the volume of a canonical pen? Volume of a cone. What's the volume of a cone? V equals to what? 1 over 3 pi r square h. Okay, 1 over 3 pi r square. So pi r square is the area, right? Area of the base, and then h is the height. But if you do pi r square h alone, is a cylinder. So it divided by 3. And divided by 3, you get this. Okay, so anyone know what do you need to do next? What should you do next? So this formula, right? Not all the R and H are variable. Someone is fixed here, right? There's one thing that you never change. That is the radius. Where radius never change. So actually it's 1 over 3 of pi of 6 square h. Okay, so we want to write volume as a function of height. And then we see how this volume change with respect to time, and then how this height change with respect to time. So this volume is with respect to ht, and then h is with respect to t. Okay. So what's the next step? dh dv, and then dv over dt equals to dh over dt, dv over dt. So, okay, let me write down it. So, dh, dv, which one first? dh over dt over dv, like this. Multiple dv over dt. What's this? This is dh over dt. Not quite right. You know what this suggests? This suggests that d over this suggests that h is in terms of v. Do we write v in terms of h or h inverse in terms of v? Which way we write our v? Sorry, we write v in terms of h. Okay, so it's better that you do this. Okay, it's better that you do this. So it's better that you do v over dt equals to dv over dh times dh over dt. Okay, so the question is dv over dh equals to dh over dv inverse? Is this true? Is this true? You sure this is true? You sure this is true? How about I rewrite the form like this? This is the actual derivative form, right? Is this true? True. I'm not sure whether it's always true or not. So that's the problem that I don't want to write derivative in the fraction form because this might not be always true. Okay, not. The first one makes sense if you can write the height in terms of volume. Okay, if you can replace your height in terms of volume, then you can do that. Okay, but I think generally the chain rule we want to use is this because we write v in terms of h. Okay, then because this tree is just number, that's why I can divide dv over dt by dv over dh at a specific time. Does that make sense? Okay, this one I'm not sure true or not. Can you prove it to me? This is true always. Let me try. No. Yeah, obviously after class. I don't think this is always true, and I don't think this is always doable. Okay, so you cannot just click it, click it. Okay, you cannot just move it across and then click it. Okay, okay. Yeah. So another thing is maybe another thing to ask yourself is so this one is I don't think always true. Let me put a warning here. Don't think always true. I think the way you think about that is maybe dv over dh times dh over dv is 1, which is also not always true. Always true as well. Okay, so be careful. That's why I say I don't think about this derivative as a fraction. Sometimes it looks like a fraction, but it's not really a fraction. Okay, it's not really a fraction, it's just an operator. But some behavior looks like fraction. Alright, for example, the chain rule, like a fraction. But don't ever think of it like this. No, it's not like that. Maybe you can use it to memorize the formula, but it's not how it came from. Okay, it's not how this thing come from. Okay, so I think it's fine, right? We leave it here and then you can finish the calculation. Okay, go to the next. So let's look at this one, how to describe this. So there's an airplane flying north at 350, 320 kilometer per hour. So let's draw the aeroplane movement. Airplane like that. No, this is quite ugly. So maybe like this. Flying north, 350, 320 km per hour. So let's call this S. So ds dt is 300 hour. Passing a town, okay, at noon. Yeah, passing a town at noon. So let's draw a town here. Maybe town like that. Okay, 12 p.m. A second airplane going to the east at 300 km per hour. Going to the east or the other direction. Let's call this U. Okay, so there's another aeroplane. Okay, so such that du over dt is 300 km per hour. So this is after 15 minutes later passing this town. So let's record the timing here. So one is 12:00 p.m. here, and then the other one is 12:15 p.m. Okay, so you could imagine that by 12:15 p.m., this green arrow, this green airplane here is still at the town, but the red airplane here already go a bit further in north, and then they keep moving. Okay, makes sense. So by 12:15 p.m., maybe it's around here already. Okay, if you can imagine a motion, then you will keep going up to the north for the red one and then green one to the east. Okay. Now the question is, if the airplanes are flying at the same altitude, okay, so same altitude is like on the same plane. Plane here meaning the same flow. Okay, same flow. How fast will they separating at the 1:15 p.m.? So what does it mean by separating here? Where's the distance? Again, the direct distance. Okay, so the separating distance actually is this distance here. So let's call it W. Okay, so if you imagine if they are not on the same floor, then you will have a different. Then you need to okay, the other dimension. But now it's like a 2D plane. Okay, so it's in the 2D plane. Okay, so you can use what formula here? How do you relate W, S, and U? So you want to find dW over dt at the time 1.15 p.m. How do you relate SU and W? Huh? How to relate? Again, Pythagoras theorem, because you can you see a big right angle triangle here? You see it? Okay, so you use Pythagoras theorem. X squared plus U squared equals to W. Okay. Sorry, W squared. All right. So if you use implicit differentiation here, what do you get? 2x dx dt plus 2u du dt equals to 2w dw dt. Okay, so do you know why we use implicit differentiation here? Because we regard all these variables as a function of t. Okay, when t changes, S will changes, U will change, W will change. Correct or not? When time goes on, you move more to the north, you move more to the east, and then the separating also get larger. Okay, all of them depend on T actually. So there's an implicit variable inside here. Okay. Oh. Okay. Yeah. So what? So where are we? Okay. So what do you want to find? We want to find dw. So this one is dw. Sorry. So if we move everything to the right hand side, then we have dw over dt equals to dx over dt plus dt, and then divide by over 2w. Okay, so the question gave you what is ds dt. So this thing is fixed. which is 320. U du dt is 300. Okay. So, but the question asks you about time at 1:15 p.m. So do you know what happens at 1:15 p.m. to SU and W? Can you calculate? So at 1:15 p.m., I gave you the velocity already. So the velocity is like never changed. There's no acceleration. So I gave you the timing. Can you compute the distance they have moved? So what do you think? At 1:15 p.m., what's your S? What's your U? What's your W? Huh? How to compute? I tell you the speed in the direction of S, and then I give you time. Can you compute the distance or not? How to compute? Yeah, sorry. Yeah, for the S, you take 320 by a quarter, you mean 1/4. Okay, why do you multiply by 1/4? Because of the 15 minutes. But, sorry. The difference between what and what? But the question 1:15 p.m. Yes. Or you mean you need to add the 320 times 1? Okay, sure. Okay. In that case, it's just 5/4, right? Okay. Yep. Okay. Okay, so everyone get this? How we get the 5/4 here? Because this is so let me write here. This is 1 point. This is, how should I put this? From 12:00 p.m. to 1:15 p.m. Okay. Okay. How about U? U is the same, right? Is it the same or not? No. Why? Why U is not the same? Okay, so because U will start at 0 at 12:15. So between 12:15 and 1:15, just 1 hour. Okay, so you should take 1 here. Okay, because this is from 12:15 p.m. to 1:15 p.m. Okay. Any question so far? Any question? So basically, we want to ask at 1:15 p.m. how much you move to the north and how much you move to the east. Okay, measure from the town. Okay, so the town you should regard it as a 0, distance 0 here. 0, okay. Okay. Okay, so from X and U, can you get W or not? Okay, so you just use the Pythagoras theorem. Okay, you take x squared plus u squared, and then you take the square root. Yeah. Okay. Question? I think some of you are quite confused. 冰针, is it 冰针? Yeah. Do you understand what I said? Have you understand? No, actually, no. No question? Okay, okay. Okay, so you just substitute everything into this solution, this question, this equation here. Okay. So the answer I computed was 436 km. Here you can substitute it back. Yeah, any question so far? So basically, what you need to put in was all the changes, rate of changes, and then you need to check the specific distance at the timing that you want to compute. Okay, and then this will contribute to the rate of change at that moment. Okay. Any question? I urge you to understand this question before you're doing it. Because if you just gonna memorize this formula thing, then I think you will always miss something when you do question. So if you understand what this question is, then you won't miss. Okay, no? Okay, any question from here? No question? No? Okay. Yeah, maybe do the last one before we take a break. So this 3.6 is also using Pythagoras theorem, so we will skip this. No, not really Pythagoras theorem. This is angle actually, because it's asking about angle. I thought it's Pythagoras theorem. Wait, let me see. In that case, we will try and do this. I'll try and do this because the last three is about angle. So there's a woman standing on a cliff. So let's draw a cliff. And then there's a woman here standing on a cliff, watching a motorboat through a telescope. So there's a board here. Not sure how to draw the board. So let's try. Again, moving to the shore. So there's a water here. So taking a telescope. So let's bring a telescope for the. Okay. So you will see this telescope. Let's say this direction. If the telescope is 100 meters above the seawater, so 100 meters from the seawater, and the ball is approaching, okay, at 8 meters per second. So the direction I draw is fine. Going 8 meters per second. At what rate is the angle? Okay, so the question is about this angle here. Or the telescope changing when the boat is 100 meters away from the shore. So again, there's another 100 meters here. Okay, so you could imagine that in this question, right? So when the boat is moving, approaching the cliff, your telescope should bring a bit downward. Depends on the rate. Okay, so let's set up the problem here. So let's set out the problem. Let's say that this displacement here, this changing variable here is s. This direction is s. And then the changing angle is theta. So I think there's really these two variable changing with time, right? So let s be the distance of the boat from the shore. And theta be the angle of the telescope. Okay. So what's the relation between angle and distance here? Anyone know? There's another right angle triangle here, right? Okay, so what's the relation? You got the opposite side and the adjacent side. So what do you get? Tangent? Tangent, right? Tangent theta equals to opposite over adjacent. Okay, so this is the function that you want to look at. Both of these are implicit with respect to time. Okay. And then what's given here, yeah? What's given here was the boat is approaching. So meaning what? ds dt, right? So by assumption, ds dt is 8 meter per second. Okay. But you want to find what is d theta dt. You want to find d theta dt at s equal to 100. Okay. So you got ds dt, d theta dt. Wait, you got ds dt, you want to find d theta dt. Okay, any relation between theta and s or no? Can you find ds d theta? Dt d theta dx? Is it possible? Yes. So what should we do? Jungjie, is it Jungjie? No, no Jungjie. Jungjie is that one. Here is what? Who is beside Jia Tang again? This side. What's your name again? Oh, you are Jungjie. Okay. I confused with Jingyi. So Jungjie. So Jungjie, what should we do here? What should we do? We have ds dt, right? We want to find d theta dt. Do we have any relation between d theta and ds? D theta ds? Uh-huh. D theta over dx, and then ds over dt equals to d theta over dt. What is this rule? What's this rule? I think we repeated a lot of times this rule this morning. Chain rule. Okay, do we just use chain rule? Okay, we just use chain rule here. So can you find what is d theta ds? Okay, you can't really write theta in terms of x, right? But we learned that we can use implicit differentiation to do it. Okay, implicit differentiation. What we're gonna do is we differentiate with respect to s on both sides. Okay, so differentiate d theta tangent theta with respect to s. Do you still remember what you get here? Sorry? Theta equal to arctangent. What do you mean? You mean write it as sine theta over cos theta and then use quotient rule? Is it? But there's a formula, you know, right? There's a formula you remember, right? So you can check back your formula. This is secant square theta of d theta of ds. And then the other side you get just 1/100. Okay, is this what we want to do here? ds over dt and then d theta over dt. I think that's fine, right? Okay, yeah. So you just put d theta over dt here, and then what's ds dt here, and then you divide by what's d theta over dx. So this is 1/100 over secant of motion. So you divide by this or you multiply by this. That's second. Okay. So you need to evaluate this at s equals to 100 meter. So you need to evaluate everything at 100. Okay. Does it make sense or not? A question? Felicia, I'm confused. Okay, yeah, ask. You should ask. Ah, you need to learn one by one. Okay, so I guess there's some learning method you need to change from your high school. Because your high school, right? Whatever teacher say, you just accept, right? Is it true? Okay. So from now onwards, right? Whatever I say, right? You should ask. You should test me. You should test me. Okay. Maybe it's not true for every lecturer here. I want to tell you some true story here. Maybe this is not true for most of the lecturer here because some of the lecturer is still kind of an Asian style. Okay. But I'm learning from Australia. So I'm a little bit different. I'm not growing up fully in Asia. Although my first part of education is like coming from Asia. So actually I changed after I grew. I mean, like I took my degree in Australia. It's really different. In Australia, right? You will often hear students debating with lecturer one. They will just ask question in class one. They just question the lecturer, and then they will discuss something that I don't know. Why I don't know because I never thought about that question yet, and then I don't know why they ask about that question. Okay, sometimes I know their question. Then I was thinking like, the question is like pretty obvious, or maybe that question is like very dumb. But nonetheless, the lecturer will always say, "That's a good question." So the lecturer will always encourage students to ask. Okay, so one thing is whenever I say something confusing or doesn't make sense, you should ask. You should ask. Yeah, because sometimes I could really say something wrong. Although I am thinking the right thing, but I might say something wrong. So that wrong thing will confuse you. Okay, so I think one thing you want to learn in this uni is you want to learn how to speak. For example, right? For example, just now I asked you how to do. Whenever I ask you how to do, you tell me some very specific thing. So for example, oh, dt over dx, ds over dt, dt over d. D theta over ds times ds over dt equals to d theta over dt. No, so why not you just tell me use change rule? One word, using change rule. Then we will know how to put these things together already. Okay or not? So I think you need to learn how to listen to instruction. Okay, not just follow instruction and then create instruction. Okay, this is a high level thinking. Okay, if you just can follow, then you just forever follow your other follow. Okay, does people know how to continue here? So you fix your x as 100 meter, and then you should be able to find your theta, right? Tangent 1, shift tangent 1. So you get your tangent, you get your theta. You get your theta, you know what is secant square theta, then you multiply by 100, then you multiply by the assumption DST. Then you will get d theta dt at this distance. Okay. So you should think here, why the question asks about x equal to 100? If you sub in into the tangent theta formula, shift tangent 1 is very easy to find. Tangent inverse 1. Tangent inverse 1 is what? What angle you evaluate to what? When sine theta equal to cos theta. When is sine theta equal to cos theta? When theta equals to pi over 4. Pi over 4. Yeah. Okay. So here is pi over 4. So we put 100 secant square pi over 4. And here's okay. Yeah. So the other two question is similar. Okay, you need to use chain rule or implicit differentiation to help you to get the answer. So it will be left as a exercise. You can try and do at home. I'll put out the solution. Okay. Any question before we jump to next section in the next hour? Any question? Any question? So the general strategy here was you want to know something related to time. You just find one formula to relate everything that you know related to time. And then you can do implicit differentiation if it is possible. And then you can use chain rule, other rule to help you to compute the derivative. Okay, I think the most challenging part for this question is how to find a formula that relate all these variables. Once you can relate all these variables together, then you can do derivative if they are nice. If they're not nice, then you need to get another way. Okay. Any question? Okay, let's break until 11:08. Yes. Yeah.
That's
Mm.
usually
Mm.
in high school
Mm.
we
Mm.
do it like it
Mm.
this way, but why didn't it work?
Because this is the average. This is the average.
I consider the time which
Mhm.
that's how we define the
Limits. I mean, like,
yeah, and
I mean, you need to take the limit, right?
Yeah.
Okay, then.
like I can't figure out the change rate of
let's
R
see.
because this is the cube of the R.
No, I mean, if you use this way, you should be able to do it. If you use this way, you should be able to do it.
What idea the limits?
Wait, why are you? Wait, what are you doing? What are you trying to do here? You got quick question.
Uh, just the
Wrong again.
yeah, I think.
You can send me. I can check.
Oh
Yeah, you just send me and then I check. If I'm wrong, I will check. Yeah, I've changed the last one. Yeah.
the
Attendance?
Yeah.
Okay, I will take it.
Okay, thank you.
Yeah.
Attendance.
Attendance. Okay, I will take it later because I haven't touched the second page yet. So what are you trying to do here? Yeah, correct. DVDT is this one. Yeah. So what's this for? What's this for?
I found it didn't work. So
No.
I
What are you?
just,
What are you trying to do?
this is the first way, and I found it. I can't deal with the right hand side, and I gave up.
Wait. What are you trying to do here? What is V0? some fixed volume.
This whole means the change in a specific little time.
Sure.
So
Then
I can't find the change rate of R, because this is the change rate of R cube. So that's why I gave up. I can't handle that.
So yeah, sure. I mean, like, yeah, there's nothing wrong about this. The problem is, yeah, there's nothing wrong about this. Yeah. Then what you want to do? So you said this is equal to 100. No.
知道它这里是半径的平方，为什么？它怎么通过半径的立方的变化率找到那个半径的变化率？它最后不是让球就这里卡住了。
Yeah, obviously, what you mean? You want to just straight away figure out?
Yeah.
You want to just figure out this one, is it? From here, you want to get this. I don't think
that works
that easy. Well, I mean, like, obviously, this is one of the factor, right? So you can rewrite this at r minus r0 of r square what? Do you know how to factorize this?
plus r 那个
What?
陈怎么说的？
Multiply
dr0.
Huh? This one I know. What's the middle one?
R
This one is
multiply
R
r0.
R times R0.
Yeah.
Enough?
Yeah.
R cube and then R cube minus R square. Oh, okay, good. Okay, yeah, good. Yeah, so then you will split into these two parts. So I think you need to assume this one exists first. And then you need to assume this one also exists first. Yeah, so you need to figure out what's this. If you can figure out this, then this one exists. Then you can combine all these, you get this. Does this exist or not?
That's really asking for trouble.
Yeah, I'm not sure this one exists or not. But based on this solution, it should exist at that point. Yes.
I try to directly calculate it, but I don't know why I get a double answer.
Double answer?
It should be 8 here.
It should be what? 18?
8.
8.
It should be 8.
Okay, so you get 6 thing only.
Yeah.
So you need to divide by 2.
Where is the 2?
Where's the 2?
Yeah.
After you differentiate this, there's a 2 coming out, right?
What?
There's a 2.
No.
Sorry. Yeah.
Yeah. So right here. This question can be solved in a geometry way.
How?
Divide the speed in. We want to figure out how they split in this way. So divide the speed into this way and the how to say this? And
how come? Oh, you mean like the you mean like the XY?
Yes. Divide them separately and plus
sure.
In
Why?
here.
Can you write in full and then send me? You write in full and then you send me. Write the full step and then you send.
That's
Yeah.
And the last one. So here it's about 这是弧度制还是角度制？ Radiation.
Yeah. You can convert to radian. But what?
How? 就是说
Radian. You can convert to radian. It's not a big deal, right?
我不知道这里算出来应该是弧度制还是角度制。
Depends on what you use. If you use pi, then it's radian. If you use 180, it's degree.
So
depends. I mean, like anything will work. Doesn't matter.
I just
Ah.
calculating this with the and I get this and I cannot figure out the 就是最后我真的算出来，我最后就不知道我这个单位是什么了。我这个步骤这么写的话
I don't think so. I mean, wait. Depend. Why you say you don't know? I'm not sure why you don't.
because there is no pi, but there.
Well, no, I mean like depend on what you give to this number here. Do you use degree or you use radian here? If you use radian here, then it's a radian. If you use degree, then degree. But I think it's the same.
Really?
Yeah.
It must be radian. If I use degree here, I can't finish the rest calculation.
So it's radian?
So it's radian.
Yeah.
I see.
Okay. Yeah, yeah. 那也结束了。这个？
这个，因为它，最后这个结果，哎，我找一下，再往上翻一下，就这儿，你这个，往上直接带上它那个6，应该是不太对的。
6是不对啊，有3下。
因为你抓
OK，Thank you。OK，你对。对。什么？
考试有个比喻，就是它那个那个 D 啥来着？DS D C 塔 D 什么来着？
哪个？
就刚最后一道题。
最后一道题。
对，刚上课时候写了个比喻，
这个
最后一步带的时候给它带了个倒进去，那不用倒。
还猜？在哪里？看一下，这里。哎喂，sorry，这边。这个？
对，你看我这带了个倒着进去，不对。
我要倒数。我不是搬过来我要除吗？我除了不是变分吗
？DC 塔 DT 啊，这是这边。
OK，谢谢。OK，很好。对，谢谢。等一下我说一说。
哪个位置？
哦，没有，不用绑过去，可以说。Desmond Tan here. Tommy here. Chong Yi. 英杰。Gopagani is here. Gopagani. Okay, you. Arthur. Is Arthur here or not? Arthur. I think I saw Arthur. Arthur. Is Arthur here? Can call up the Arthur. Who is beside Arthur? Who is beside Arthur? Don't know. Okay, let me call him. Arianto. Hisham. Daniel. Hashim. Where's Hashim? I think Hashim sick. Madia. Yeah. Aaron. Brandon. Alicia Scott. Gunaganti, not here. Margaret, Lip. Hassan Khalid, being sick. Jahil, I think Jahil not here. Javed, okay. Gabriel, is Gabriel here? Oh, Gabriel, yeah, right. Jeffrey, is Jeffrey here? Jeffrey, good. Purity, God. Yeah. Chen Fan. Ya Ting. Is Ya Ting here? Oh, Ya Ting. Not here. Hu Ye. Is Hu Ye here? Not here. Guo Hongliang. Okay. Hey, can I ask Chen Fan and Guo Hongliang? You guys are retake, right? I think your result is pretty good. Or why are you retaking this class? Huh? Not good? You're previously not good? What do you get? Did you fail this course or not? No fail. You? Did you fail this course? Not good enough. You want to get better, so I see. Because I see your quiz is quite good, so I was like curious, what are you doing this again. Yeah. Okay. Oh, we are someone coming from different class at the back. Hey, who are you? With hand. Yeah. Desmond, huh? Can you call up after? Hey, Arthur. Hi. Arthur, did you manage to submit your quiz? Yeah? I didn't get it in the Moodle. Where did you submit it? It's not on Moodle. Can you check your Moodle submission? I didn't submit. I didn't get it from you. So please check. Yeah, please check your Moodle. I'm not sure what's wrong. There's nothing from you. Okay, so thanks for the checking by Haorang. So it is not true that we can just substitute r equals to 6 here, because this volume, when you change, right, when the height changing, the water increasing, the radius is also increasing. But you will do this substitution when you want to check at height equals to 4 meter. Okay, so this is the volume at the height equal to 4 meter. Okay, in general, this radius is not changing. I mean, it's changing with respect to time. Okay, but if you want to differentiate with respect to h, right? If you want to differentiate with respect to h, so what should you do? What should you do here? There are 3 variables here. You cannot just differentiate with respect to h, right? So any relation between h and r here. Actually, there's secretly a linear relation between h and r here. Okay, so there's another secret relation that you need to figure out, which is okay. Let me move everything else down. So let's move this h part down. Okay, so this is holding about. This is everything about this, right? Okay, so there's actually another secret relation about v and h. So what's that secret relation here? So that actually h is equals to 2r. It's such that r is equals to h over 2. Okay, such that v is equal to 1 over 3 of h over 2 squared over h, which is I over h cubed over 6. Okay, not 6, right? 12. Okay, only then you can do what is dv over dh. So maybe you will ask a question, how do I get h equals to 2r? Do you know how to get it? Maybe in high school, the lecturer, the teacher will tell you that, because h equals to 12 meter and then r equals to 6, so h equals 2 times r. Is it what you do in high school? You have this kind of question in high school. I think I do it before in high school. The lecturer, the teacher will tell us like, because h equals to 12, cm, 12 meter, and then r equals to 6 meter. So there's a linear relation. True? True. Is it true? Not true. Depends. Don't know. Never do. Never do this kind of question before. Oh, okay, okay. So it do never do before. China do this kind of question before. But so how do you figure out h equals to 2r? What did the teacher tell you? How to figure out? Huh? What's familiar triangle? Similar triangle. Ah, similar triangle. Oh, similar triangle. Yeah, makes sense. Okay, similar triangle. Yeah. So there's a big triangle here, right? Okay, so here's 6 meter, here's 12 meter, and then how to use a similar triangle? So there's a small increasing triangle, right? So then what? Why? We're trying to explain that, right? So similar rectangle just says what? So let's call this what name is it? Okay. So well, I think we just put it R and H here, right? So similar triangle tells you that the ratio of R over H is equals to 6 over 12, like that, right? Okay, so that's how you get this ratio here. Okay, R equals to 1 over 2H. Okay, makes sense, huh? So this is the ratio. This is the similar triangle, right? By similar triangle. Okay. Okay, this part done. There's one part that I do extra stuff right here. We don't need to divide, multiply, right? This is still division here. Okay, so still keep it downstairs. Okay, that's it. All right, let's continue to this one. Okay, so this is the very last part, chapter 3. So linear approximation. Okay, so what's the idea of linear approximation here? So the idea was you have a curve, right? Okay, and then you have a tangent line drawn here. Okay, so when you zoom big enough, this tangent line is really like a linear line. Can you see or not? The curve actually like coincide with this line here. So when you get very close to the point you make the tangent line, your curve is actually linear. It's just a straight line. You cannot see curve. You just see straight line. Okay. If you zoom big enough. So what do we mean by that is, what do we mean by that was you can actually estimate the gradient, okay, at that point by some x nearby. Okay, by some x nearby. Okay, throw the limit away. Okay, you just remove the limit. Okay, you can use some specific x nearby x. Okay, to find this f prime a. Can you see that this approximation here is actually the gradient formula? Okay, it's not quite equal because we need to do limit. But if you take x close enough, this is how you get fx. And this is how you can find the fx. And this is what we call a linearization here. Okay, it's not quite fx, but something very close to fx. Okay, it's not quite the fx, but something close to fx. Okay, so do we have picture here? Yeah, we got a picture here. Okay. Okay, so maybe let's say if you want to evaluate what's the fx here. Okay, what's the fx here? So let's say what's the fx here? Fx is this one. So maybe call this b because we got a here. It's a. So you want to figure out what is fb. Okay, the point of linearization here says that you can use your gradient line, okay, to find your FB. It's not very far away. It's not very far away. But can you imagine that if B get further from A, then the value of FB and linearization of B will be very large. Okay, when it is close, you see, when it is close, these two numbers actually the same. Okay, very close to each other. Makes sense or not? Okay, when it is close, you just use your tangent line to compute it. It's easier. Because sometimes you can imagine that the function is like a lot of square root, something else, right? Okay, but equation of line is just putting in the derivative and then putting in the x, and then you will get the y. Okay, now, can you see? When this b is close to a, is really what you get from your tangent. Okay, but it's far, it's no use. Okay, linearization doesn't work for far points. Okay, only points near to a. Okay, near to a is a very good approximation. Away from a, then the distance is getting larger, larger, and larger. Okay, it's not good. Okay, but nearby is okay. Okay, so let's see how we're gonna use this. Let's see how we're gonna use this. Yeah. So let's see how we're gonna apply this. So find approximation for square root 5.6 and square root 8.7 without calculator. Okay, without calculator. So this is about approximation of a square root of a number. So the function you should consider is a square root function. So to get linearization, right? So you want to get a tangent line. So first thing to get tangent line is to get the gradient first, okay, and also the point you want to make the the tangent line. So let's get the gradient. Okay, so where you should consider, yeah, where should you consider? Where should you consider if you want to find square root 4.6? Which point that you know how to do square root is close to square root 4.6? 4, huh? Okay, so let's consider linearization at 4. Okay, so let's do this shape. So we have square root x here, okay, and then we know how to do at 4. 4 maybe give me a 2 here, okay, but now I need to evaluate what is 4.6. Okay, so instead I go and do what is square root 4.6. I'm gonna use the linearization, okay, the tangent line, to find what is the approximation of this square root 4.6 here. So we want to find L 4.6. So then if we consider the linearization there, is Lx plus, sorry, Lx equals to f4 plus the derivative of f at 4 times x minus 4. Okay, because this is the point we do the tangent line. So 4 f4. Okay, no? So this is relatively easier to compute because we know what is f4, and then plus some a little bit coming from your derivative. So all together, what do you get? What's this line here? 2 plus 1 over 4 x minus 1 over 4 times 4 is minus 1 plus 2 is 1. Okay. Hence, I don't know how to compute square root 4.6, but never mind. I get something very close to 4.6, which is 1 plus 1 over 4 times 4.6. Okay, which is what? which is 1 plus 4, 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 5, 20. So it's 2.15. Okay. Go and try. Do you have calculator? You can type in square root 4.6. How far it deviate? Can you tell me how far it deviate? Square root 4.6. Should be 2.1 something. But 5. Can you continue further? 2.14, 4, 7, 6, 1, 0. Okay, good enough. Okay, so you can see that it deviate a bit, but it's good enough already. That is good enough to see it is 2.1 something. That is good enough. Okay. Obviously, you don't go and pick square root like 9. You want to try what happens if we do linearization at 9 and then see what it gives for square root 4.6. You will expect a larger error. You want to try? Let's try. Okay, let's try. We do consider linearization at 4. And then we see what is square root 4.6 from there. Okay, so let's try that. So if we do linearization at 9, we'll get the tangent line at 9, F9. F9 is 3, right? So this one will square root 9, x minus 9. Okay, 3 plus 1 over 6 of x minus 9. Let's keep it like that first. We can do computation here. So if we do square root 4.6, which is L of 4.6, then 3 plus 1 over 6 of 4.6 minus 9 is what? Can someone quickly compute this? What's this? 3 plus 1 over 6 and 4.6. What's this? What's this? Negative 4.4. Is it divisible by 6 or this thing? 6, 6, 0, 6, no, 7, 7, 20, 20, 6, 6, 6 divide 20. Cannot divisible finish, right? 0.777, 0.733333 something, right? Okay, so 3 minus 0.733333, what do you get? 2 point 2 point 2 point what? Jingjie, what do you say? 2.6 2.2 6 6 6 6 6 6 6. Okay, you can see that. You see, if you do linearization at a further point, you see the error you get is larger. Okay, it's pretty large. Okay, but let's say if you use the linearization to do approximation for square root 8.7, then it's good. It's better than use the linearization at 4. Okay, so can you do this yourself? You can try and use this linearization at 9 to do square root at 0.7. Okay, so if it is good, then the tangent line is very good for you to compute the approximation. You no need to put the actual value back to your function. Okay, so next from this idea, right, we will introduce something called the differentials. Okay, so we will differentiate what is delta x and dx. Okay, so delta x and dx. So let's use this picture to tell you. So if you look at the y is the blue curve, and then the red line is the tangent line at SFX. So the dy is the changes between the point you evaluate at tangent line with what? With fx. Okay, but the delta x is the actual change in your function value. Okay, you put your x into your put your x plus delta x into your fx. So let me write down here. So delta y is equal to f of x plus delta x minus fx. But dy, let's call this Lx, this line, tangent line here. This line here is L of x plus delta x minus fx. Okay, so you will expect that dy is a bit larger than the delta y. Depends, actually depends. It depends on what curve you get. And then the dx is always the same as the delta. Dx is always the same. Okay, but from what we discussed just now was dy will be equals to delta f prime x times dx. Okay, because this is just the change in y over change in x equals to the gradient. Okay, this is the nice thing about the tangent line. Okay, so far okay or not? So you need to differentiate what is dy and delta y. Delta y coming from the actual function value, but dy coming from the change with the tangent line and the original point. Okay, can differentiate this. Okay, because the nice thing about this dy over dx is you can always express dy over dx as the derivative. Correct or not? This is what we learned last time, right? But we never learned what is dy, what is dx. Okay, but now you can interpret the dy as a change the distance between the tangent line with the actual point. And then dx is the change in x direction. Dy change in the y direction. Okay. Does it make sense? Because in the usual case, right, delta x over delta y over delta x equals to m only works for linear line. Okay. So that's why we have this dy dx work for tangent. Okay. All right. Let's try a question to check that whether we understand about this delta y or dy or not. So how to get delta y and how to get dy. So first, we are given the function x cubed plus x squared minus 2x plus 1. Okay. And then we are given the change in x from 0.2.05 to 2, which is 0.05. Okay. Delta x is also equal to dx. Okay, so how do we compute delta y here? Okay, it's exactly f of 0.5 minus f2. Okay, it's just comparing, okay, comparing the y value at 2 and 2.05. So if you do the calculation, okay, you can go and expand it. I think you should use calculator because the solution you get is 0.717625. Okay, but how about getting dy? So remember that our dy is coming from the tangent line. Okay, so dy equals to f prime x dx. So you need to get your f prime x first. So f prime x in this case is very simple because you are differentiating what's this, polynomial. Okay, so just get 3x squared plus 2x minus 2. So then to get dy, you just put it in. So what's your f prime x? Where should you evaluate at? What do you think? Should you evaluate at 2 or 2.05? Is it 2 or 2.05? Which one should you pick? So there's a direction problem here. Are you drawing your tangent line at 2 or 2.05? It's actually at 2. Okay, because the changes is going from 2 to 2.05. If the changes is from 2.05 to 2, then you need to do your tangent line at 2.05. Okay. Then dx is 0.054 in our case. So if you put all things together, 3.2 squared plus 2 minus 2 times 0.05, then this is 14 times 0.05, which is 0.7. So what can you see here? So you can see here that, observe that actually dy is less than delta y. Okay, dy is a bit less than delta, but dy is almost delta y. So in this case, can you see what happened here? Your tangent line actually go lower than your actual curve because your dy is smaller than your delta y. So your tangent line go lower than your actual curve. Should we plot this for you to see? Maybe let's plot this for you to see. S cubed plus x squared minus 2x plus 1. X cubed plus what? Alicia. X squared minus 2x plus 1. Wait, at the top. Minus 2x plus 1. Minus 2x plus 1. Okay, so this one, close it and place. Okay, so where are we? We are doing at 2, right? Okay, so let's fix around 2 here, and then we try and draw tangent line from here. Oh, shit. I accidentally clear everything. Can I undo? No, undo. Okay, so it's a x cubed plus square minus x squared minus 2x plus 1. So export this one. Paste here. So let's make it bigger. Okay, so they want to do it at where? F2, right? Oh, it's not enough for doing F2. Let's see. Oh, it's quite big here. Okay, sure. So let's export from here. Okay, so if you attempt to draw the tangent line here, okay, 0 to 0.2, okay, you can kind of see like, where's 2? 2 is here. Then, oh, a bit hard to draw. So the tangent line was really linear here. The tangent line should go lower. Should go lower like that. Okay, maybe I draw like this. Where's here? Maybe zoom in here. So the tangent line go lower the curve like that. So here is 2, right? Really draw a straight line. Maybe it's better. Okay. So your dy here. So this is your dy, but your delta y is a bit further. Okay. Yeah. Okay. Yeah, sure. Okay, how about next one? Okay, how to apply to real life. So let's say we want to approximate the increase in the area of a soap bubble. So this soap bubble, I think they are assuming it is a spherical. So we want to talk about the area of a soap bubble. Is A equals to 4 pi r squared. Okay. So then now we just want to approximate. Okay, we don't want to compute the actual thing. If you want to compute the actual thing, you just put r equals to 3, r equals to 3.025, and then you take the difference in A. Then that's the difference. But we just want to approximate it, okay, so that you don't need to deal with these square calculation. Okay, so how we're going to do that? So let's get the delta r first. So delta r is 3.025 minus 3, which is 0.025. Okay. But then what do you need to get? You want to get dA, right? So dA is 2. So you need to get what is A dA over dr. You guys confused if I write this? You guys confused? Would you confuse? Or maybe better, if it is better, I write this. Now better? Better. Okay, you differentiate the function with respect to r. But the dA and the dr on that two things is really some changes going on. Okay, so this is how you want to view it as a fractional. Okay, just now, is it what's your name again? Jia Seng, huh? Okay, this is what Jia Seng suggests just now. Why can we view this operation as a fraction here? It's really the changes in the tangent line with the actual value in y direction and then x direction. Okay, if you want to view it like that. But chain rule is not coming from here, but this one is another definitely equation. Okay, so from here we get that 8 pi r times dr. Okay, but then where did you make your tangent line? You make your tangent line at r equals to 3, and then dr is 0.025. So altogether you get 0.6 pi cm squared. Okay. Can someone go and compute what is this? Can someone go and compute what is delta A? So delta A is 4 pi 0.025 square minus 4 pi times 3 square. Hey, okay, sorry, this one is 3 point. Okay, can someone compute what is this? With pi? Maybe with 4 pi. Okay, maybe tell me what is 3.025 square minus 3 square. What's this? Can someone tell me this? Calculator. What do you get? 4 pi times what? So what's the difference between these two square here? 0.150625. Okay. So wait, let me see how close are they. So if you multiply by 4, what do you get? 0.60249. No, not 9. I think so 500 like that. Is it? Okay, so you differ by differ by a factor of 0.0025 and blah 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 so on. Okay, so it's good enough already. So it's good enough. Okay, so you can just see the difference between these two calculations. One calculation you need to compute the square difference of square, but one calculation is you just need to get the change in R, and then you need to know how to do your derivative, and then you just need to know where you want to do your tangent line. That's it. Okay, you see this step, less calculator. Above, you need a computer to help you. Okay? Yeah, depends on what you want. Okay, it's good enough answer already. This is the differentiation. Okay, any other question? I think there are two more questions left. Let me for you. A question? No? Okay, so this is one of the instant, if you want to see your derivative as a fraction, this is how you see it. Okay, it's the changes between the tangent line with the actual value. The ratio you get from your tangent line with the actual. Already, really is just the ratio of your tangent line, actually, because that point is lying on your tangent line as well. Okay, so this thing only works if you increase your radius by a small amount. If you increase your radius by 100, you can throw this method away already. You understand or not? Okay, if this 100, because your function is not linear, so you cannot get everything from linear graph. But the point here is, every curve, when you zoom big enough, it is linear. When you zoom big enough, then we get very close. Yeah. Make sense or not? Do you realize that? Okay, last thing. Do you realize that the Earth you live on is actually not flat? It's actually not flat. If you go from, if you see the NASA photo, or you go out from this Earth, it is spherical. But now, when you walk on this, like for example, this university, do you feel the curve or not? No, right? You feel it? Oh no, that one is because our mountain, okay? But in general, it's not. It's flat. In general, it's flat, okay? In general, it's flat, okay? So because you zoom big enough, when you are just living on one patch, you zoom big enough, so it is flat. Okay, so zoom big enough, a line is just a straight line. Okay, if you zoom big enough. Okay, so see you next Wednesday. So if you find any problem, please just message me. Okay, just message me. Yes. Which one?
163.
63.